Hello everyone, welcome to the first of 3 videos for chapter 14 in the book by Knight. The first 2 videos will cover fluid statics and the third video will do fluid dynamics. This first fluid statics one will just do the basics, and then the second part we'll reserve for Pascal's principle and Archimedes' principle. Okay, so you'll see on the right here, so on the left I'll just kind of go through the sections that we're covering in the textbook. And on the right here, I'll have some notes. One of the main questions we want to be able to answer is, why does water stay in a cup? It sounds very basic, but if you look at just a cube of water, it has some weight, mg. So you might wonder, well, what's the force that's counteracting mg to keep it in equilibrium? So I guess to ruin the surprise, what's going on is that there's, so the water just above the cube is pushing down on it. The water to the side is also pushing on it. The water to the side is pushing on it. And you'll notice that these arrows are growing in magnitude the deeper I go inside the water. So these arrows that are pointing to the right and the arrows that are pointing to the left cancel, but the ones above and below do not. So you'll see that there's a net upward force. So we'll describe the net upward force in the next video, but for now we want to be able to describe this thing called pressure, and how it varies with depth. That will be the last thing covered in this video. So the magnitude of these arrows and how you can compute, how big these forces are depending on how deep you are in the liquid. So this depth will be d, where d equals 0 is the surface. Okay, so we'll get to that in a bit. But we need to cover some basic terms first, density and pressure, and then we can talk about pressure versus depth in the fluid. Okay, so the first one, density. So later on in the course, we're going to be talking about 2 different kinds of density, number density versus mass density. Right now, though, when I just use the word density, it's always going to be mass density. So at least for this chapter, they're the same thing. And so the symbol that we're going to use is rho, and this is going to be mass per unit volume. So the total mass of something divided by the total volume of something, or m over v. So the SI units of this quantity are going to be kilograms, the SI unit for mass, divided by the SI unit for volume, which is cubic meters. So you got to be a little careful here, because if you've taken a lot of chemistry classes, you've talked about other non-SI units for mass density. So things like grams per cubic centimeters, which is actually the same thing as grams per milliliter. Those are not the SI values. So later on in this chapter, we're going to have some formula involving this quantity rho. And you want to make sure you're plugging in SI units if you're plugging in SI units for everything else in the formula. So just as a warning, water has a mass density of, so you might have seen it as 1 in the past, but this is grams per cubic centimeter. That's non-SI, so you want to kind of get rid of this in your mind. And you want to replace it with 1,000 kilograms per cubic meter. So I expect you to be able to do conversions like this. I think grams and kilograms you're comfortable with. For liters and cubic meters, you might want to remember one fact, and that is that there's 1,000 liters in 1 cubic meter. So a liter is 1 centimeter, parentheses, 1 centimeter cubed. 10 centimeters in parentheses cubed. So this is, so you could remember that conversion factor, or 1 liter is 10 centimeters cubed. Both of these are equivalent. Okay, so something I want to mention now that's not really emphasized in the book, but something I want that will be useful later for thermodynamics, is the difference between an extensive and an intensive variable. Okay, so first of all, I'm just going to mention that rho is an intensive variable, whereas mass and volume are extensive variables. Tensive variables. And this one's an intensive variable. So what does that mean? Okay, so suppose I had a bar of gold. Gold. So it has some mass and some volume, and therefore if I divide one divided by the other, it has some density. Right? So that's all fine. And then what if I had 2 bars of gold? Just one right next to it. Gold. 2 golds. And I treat this as one new bar of gold, right? So what, in other words, so if I double the system, if I make another identical copy of the system and then put the 2 side by side and then just consider that as my new system, what things will double? So in this case, the mass will double. So mass doubles. And the volume doubles. But if I take the ratio of the two, so if I look at this this formula right here, if the numerator doubles and the denominator doubles, the density remains the same, right? So even though the mass doubles and the volume doubles, the density remains the same. Density remains the same. So the density is a property of gold that doesn't depend on how much gold you have. So density of gold is some constant value that's something like 18 times the density of water. So for the same volume of water and gold, the gold will weigh 18 times as much. So yeah, there's a table here in the book that lists some values, and notice how water has the 1,000. So they listed this in SI units. The highest that they listed is mercury, which is 13.6 times the density of water. Gold is even more. Gold is close to like the maximum density you can get. There's only a couple very rare elements, and you got to prepare them specially to get anything bigger than gold. Okay, so I think we're good on density. So now pressure. Okay, so the textbook says pressure is a word we all know and use. So they give an example of poking a hole at varying depths in a glass of water. The lower you poke a hole, the faster water will shoot out. So it's some property of the fluid. And by the way, fluid is either a gas or a liquid, which the textbook points out earlier. It's a property of the fluid that increases as we go down. And it has something to do with forces. So I really like this picture. So it imagines that you have a little measuring device where it's like a little piston, and it can measure how much you're pushing against the piston. And it's nice because if you think about taking this contraption, this really tiny contraption, and you lower it in the fluid, you would notice that the piston gets more and more compressed the deeper this thing goes. So we're imagining that there's air inside the piston, and then it's exposed to the water on the outside, and so that we can keep those two separate. And the lower the more you lower this contraption into the fluid, the more that the fluid presses on the piston. And it doesn't matter how it's oriented. So pressure is this thing, it's related to force, and it acts in any direction. And it seems to increase as we go lower and lower into a fluid. Okay. So this is the key equation right here. Pressure is force per unit area. So pressure is force per unit area. So we have an area of, right here it would be the piston surface. And the force is directly against that. Okay, so you might see this formula as written as F perpendicular. So perpendicular to the plane of the surface. If you continue on in engineering, mechanical engineering or related disciplines, you'll talk about other components of forces that are related to things like shear. But we're not talking about that here. Here we're just talking about the perpendicular component for pressure. Okay, so causes of pressure. Now we're going to, so on Earth here, you might have seen, so you're going to run into this constant a lot, atmospheric pressure. And I'll be using P naught a lot for this. So this will be in SI units. This is a really big number. Okay, so the force is on the numerator, area is on the denominator. So it's going to be some number of newtons per square meter, right? Those will be the SI units that we have here for pressure. So I'm going to write this number down, and I'll explain what it means in just a second. 1.01 times 10 to the fifth. Huge, huge number, right? 100,000 newtons per square meter. So one thing I just want to point out is that they give there's another word for this unit. So just newtons per square meter is given the word Pascal. So 1 Pascal is equal to 1 Newton per square meter. So you also see this written as 1.01 times 10 to the 5 pascals. And what this means is that, so you have the Earth, and suppose you had 1 square meter. So something like, so 3 feet by 3 feet, patch of the Earth. So what we're saying here is that there's a force acting on this area, pressing down, and it's actually pretty big, right? It's 100,000 newtons. So for that 1 square meter, so if I just plug in that area into this formula for pressure, so I plug in the P naught for the pressure, and I plug in 1 square meter for area, it's a huge, huge force, right? 10 to the 5th newtons almost. So what that is it's actually the weight of all of the air molecules right above. So they decrease as you go up into space. But the weight of all of that, so if we just looked at a column of air right above the Earth, and we weighed that, it actually weighs a lot. So you're not used to how big these forces are day to day, because you also, so for a person standing here, you might say, well, what's going on? How come I'm not crushed by this? Well, this huge, huge force that's pushing down on you is also pushing up on you right here. So you might say, well, why don't I get squished? Well, inside your body is also atmospheric pressure that's pushing out on your skin just as much as the air is pushing in on your skin. It's like the air inside your lungs are also at 1 atm. So you don't really notice this. The only time you notice this is if you, suppose you had some vacuum and you put your hand above it, you feel your hand getting sucked into the vacuum, right? Well, there's not actually a force that's acting on you from the vacuum. There's a little bit less air inside the vacuum. It's a little bit less than atmospheric pressure. And then there's atmospheric pressure on the other side of your hand. So you wind up getting sucked in because there's more air pushing on your hand. Okay, so that's a good starting point for now. So they mentioned this important number, we'll see the utility of as we go on in the textbook. Okay, and the main question we want to answer though is pressure in liquids. So pressure as a function of depth. So back to this picture right here. And to ruin the surprise, let me give you the formula here. So pressure versus depth. So if we have some any fluid right here, and this is exposed to atmospheric pressure. So you might see atmospheric pressure, so you might see atmosphere, or you might just see it labeled as P naught for atmosphere. And then you have some fluid in here. And we're looking at some point that's a depth D. Then the pressure is equal to whatever the pressure is at the surface, and then the pressure increases linearly with the depth in the fluid, rho g d. So here, rho is the mass density of the fluid. Mass density of the fluid that we're going deeper in. So here it would be, you can imagine water here. I'm plugging in 1,000 kilograms per cubic meter. G is 9.8 meters per second squared, the gravitational acceleration on Earth. And then d is how far we go into the fluid. So why is this equation true? It's exactly what it needs to be. This is the exact amount that pressure needs to be as we get deeper in order for this cube to stay put. So we already had a sense before that the pressure needed to be bigger as we got deeper and deeper into the fluid just to support the weight of this thing. So this is gravitational pressure. It's this pressure wouldn't exist in space, right? If you had fluid in space, there's no reason for it to get more and more pressure as you get deeper. And if we took this glass of water and we took it to the moon, then this gravitational constant would be less, right? You wouldn't need to gain pressure as quickly as you got deeper because there's less weight on the moon. So this on Earth would be 9.8 meters per second squared. Yeah, one example. So let me throw in a. So I want to go over this example right here in the book. So figure 14.11. Okay, so there are two important things to keep in mind when you're solving problems involving pressure in a fluid. And there are these bolded statements right here. Okay, a connected fluid in hydrostatic equilibrium rises to the same height in all open regions of the container. So I'm looking at the left right here in the first bolded statement. So it looks like, based on this picture, so in this problem it's saying, is this possible? So the first thing we want to notice is that the water levels are not the same height. And so if these are open, if this and this are open, let me get this out of the way, are open to atmosphere, then no, then this is impossible. Right? If they were both open to atmosphere, then, just based on that statement, the connected fluid will rise to the same height. So obviously both sides can't be open. Okay, let's imagine one of the sides is closed though. Then this would be possible. So if at least one of these sides is closed. So let's imagine this side right here is closed, but this part is open to the atmosphere. So I'm going to label this part as pressure P naught. So it's pressure P naught here, it's pressure P naught here. Why? Well, if we go back to this formula, so this is the mass density of the fluid. Rho for water is 1,000 kilograms per cubic meter. Rho for air is only about 1.2 at sea level kilograms per cubic meter, which actually is kind of big if you think about how big your apartment is. The air weighs more than you might think it would. But in terms of a problem like this, you don't change the fluid, the pressure isn't going to change from here to here as much as it changes from here to here, just because the density of the air is so much less than the density of the fluid. So we can basically assume in a problem that's dealing with a liquid like this, where the density is so much bigger than the density for gas, that the density here, or the pressure here is equal to the pressure here. That's all equal to open atmospheric pressure. Okay. So let's go back to the textbook right here and look at the second bolded statement. The pressure is the same at all points on a horizontal line through a connected liquid in a hydrostatic equilibrium. So what that means is if I draw a horizontal line right here, if this thing is in equilibrium, so we waited a bunch of time and let this thing settle to its happy values, to wherever it wants to stay. It looks like the column on the right is higher than the column on the left, right? So pressure is at the same, but the pressure on this horizontal line is the same. So pressure is the same along this line. Pressure is the same along this line. Okay, so if we call the pressure inside here P1, the pressure here is P1, the pressure here is P1 here, remember, because it's all the same gas, and we're saying that the pressure doesn't change all that much in a gas as compared to the liquid. So the pressure right here is P1. That means the pressure here is P1. But that's different than P naught way up here. Right? And to relate these two, we can start right here, where the pressure is P naught, and then we can add in the depth right here. So it looks like this distance right here is D1 minus D2. D1 looks like it's bigger than D2, so D1 minus D2 is a positive quantity. Okay, so that'll be the depth that we go into the liquid on the right there. So it looks like if we start at P naught, That's this point right here. And then we go rho g times d1 minus d2. That's the depth in the liquid, according to this. Then that's equal to the pressure right here, which is equal, because of the second bolded statement in the textbook, to the pressure right here, which is the pressure P1, the pressure inside this closed cylinder on the left-hand side here. This is equal to P1. So we already saw before, this is a positive quantity. This is positive. And then obviously the density and the gravitational constant are positive. So P naught plus a positive quantity equals P1. P1 is greater than P naught. So the pressure in this closed cylinder is greater than atmospheric pressure, which kind of makes sense. It looks like, you have to close this and then sort of blow in here, or get more air in here, or get more pressure in here to shoot this column of liquid up a little bit. If this was just open and then you close it, if it was in equilibrium before, these would be at the same height because they were both open. And then you close it, nothing would change. So you have to increase the pressure here to get this to come up a little bit. So you can see, so it makes sense that P1 is greater than P naught. This formula lets us calculate it by exactly how much, which is nice.